Good evening, everyone. Am I audible?
Yes, sir.
Yes, sir.
Good. So let's get started. So what was the last topic we saw yesterday?
So
Sir, we saw
between
about the relation between electrostatic potential and electric fields.
Okay. And we solved a problem also based on it, right?
yes, sir.
Yes, sir.
Okay. Yeah, this was the last concept we discussed yesterday. And the problem that we did was this thing, 2.3, right? So now write down the next topic, that is so the next topic is going to be potential energy of a dipole in an electric field. So it is going to be potential energy of a dipole in an electric field. So done. Now, so here if you see, there is going to be electric field existing. And there is a dipole placed in this electric field, right? So let's say the distance between them is 2a, right? So there will be a force of QE acting in this direction, and there will be another force of QE acting in the opposite direction, right? Now, if I take this to be a reference line, and let's say the dipole is inclined at an angle theta with respect to the electric field, then it is going to experience a torque of how much value? It is going to experience a torque of PE sine theta, right? Now, if I take the system and slightly disturb in this way, let's say this dipole is rotated through a small angle d theta. What I'm saying is dipole is rotated through a small angle d theta, then what happens is there will be a small amount of work that is done, which is dw, which is given by the expression tau d theta, right? It is given by the expression tau d theta, which is going to be PE sine theta multiplied with d theta. Because like how you calculate the work as the product of force and displacement, here we are going to calculate it as the product of torque and displacement. So this is a small amount of work that is being done on this system, right? So for me to calculate the total amount of work, we need to integrate it. So integral of PE sine theta d theta from theta 1 to theta 2 is going to be equal to PE into integral of sine theta d theta from theta 1 to theta 2. So then W will be equal to PE into integral of sine theta is going to be minus cos theta from theta 1 to theta 2, right? So if I take the minus sign outside, I'm going to have minus PE into cos theta 2 minus cos theta 1. So I took this minus sign outside and I substituted the upper limit and the lower limit. I got minus PE into cos theta 2 minus cos theta 1. Hence, The total work done by the system in this scenario is going to be minus PE into, okay. So if I take theta 1 to be 90 degrees initially, let's say the dipole was like this, then when you rotate it to some angle theta 2, then what will happen is W will be equal to minus PE into cos theta 2. Okay. So from this, what you can say is it is going to be minus P vector dot E vector. So this is going to be the work that is being done on the dipole, and this is what is going to get stored in the form of electrostatic potential energy, right? So this is what the heading is: potential energy of a dipole placed in external electric field. Okay. So having said this, make a note of it. Yeah. So are you done copying?
Sir, last.
Yeah, yeah, right. Yeah. Now you're done?
Yes, sir.
Okay. So see, there is a problem based on this concept. Let's try to solve this. Example 2.6. A molecule of a substance has permanent electric dipole moment of 10 power minus 29 coulometer, right? A mole of the substance is polarized at low temperature by applying strong electrostatic field. By applying strong electrostatic field of magnitude how much? 10 power 6 volt per meter. the direction of the field is suddenly changed by an angle of 60 degrees. So theta is equal to 60 degrees, right? Estimate the heat released by the substance in aligning its dipole along the new direction of the field. For simplicity, assume 100% polarization of the sample. Okay. Now see what is going to happen is heat is again here going to appear because of the change in potential energy. Right? So initially if you take U value of E is 10 power 6 into cos theta 1. So initially the value of theta 1 would be 0, right? So cos theta 1 is going to be equal to how much? Cos 0 degrees. Am I clear with this? So how much is this going to be? So this is going to be 10 power minus 9, 29 into 10 power 6. So it is going to be 10 power minus 23. Okay. This is the value of potential energy for one molecule. But how much substance is present? There is 1 mole of the substance. So how much should I multiply this with? This should be multiplied with the Avogadro number, which is 6.023 into 10 power 23. Can I take it as 6 itself? So 6 into 10 power 23. The answer here is going to be negative of 6 joule. Right. Now, what is the value of U2? Using the same procedure, okay, calculate and tell me how much is the value of U2 going to come out to be. Don't look at the solution. Okay, so U2 is how much? 10 power minus 29 into 10 power 6 into cos 60, right? That is going to be 10 power minus 23 multiplied with 6 into 10 power 23 into what the value of cos 60, it is going to be half. I multiplied the 6 into 10 power 23 for the Avogadro number. So 2 will cancel this 3 times, 10 power minus 23 and 10 power 23 are gone. So you will get minus 3 joule. So what is going to be the change in potential energy? Delta U is going to be equal to U2 minus U1. So minus 3 minus of minus 6, it is going to be 3 joule. So 3 joule is the amount of heat that is getting released. So I hope you could understand this.
Yes, sir.
Okay. So this is how we solve this problem. Did you all complete it?
7 minutes.
Yeah.
Yes, sir.
Next. The next concept that we are going to discuss is electrostatics of conductors. Okay. So this will be, as we know, the name of the chapter, that is electric charges, electrostatic potential and capacitance, right? So for us to understand about the device named as capacitor, right, we need to know certain facts that are related to the electrostatics of conductor. Then we'll see what are the electrostatics of another material called as dielectric. We'll combine these two and come up with an idea of how capacitors work. Okay. So when I talk about the electrostatics of conductors, there are 6 points that we are going to understand about it. The first point says, inside a conductor, electrostatic field is 0. So basically what we are trying to say here is, see, the first point says, inside a conductor, the electrostatic field is 0. So basically, when I take a conductor like this, right, and if I take this conductor and place it in the external electric field in this way, and place it in the external electric field in this way, the first point that is to be noted is the electron has free charge carriers. That is, they have the electrons present, right? They have the free charge carriers, and this electric field gets penetrated into the conductor itself. So when it happens, right, the free charge carriers, that is the electrons that are present, will start experiencing force. Now observe, this electric field, the outside electric field which I have taken is from left to right. So it clearly indicates that left side is positive and right side is negative, because electric field is always away from the positive charge and towards the negative charge. But what is present inside a conductor? Inside a conductor, you have electrons. So those electrons start experiencing force in the leftward direction, right? As a result of which, all the electrons will get drifted to the left. Similarly, when there is a deficiency of negative charge on one side, the other side will. So when you talk about this kind of a system, right, this electric field which is from left to right is the electric field due to the external factor. But due to this kind of an arrangement where the negative charges get drifted to the left and the positive charges are drifted to the right, there will be an electric field that will get induced inside, which is exactly in the direction opposite to the induced. Okay, and this process will be very quick in such a way that when you try to calculate the net value of electric field, it comes out to be E minus E in, which is going to be a 0. Okay, the net electric. Okay, so this is of inside a conductor, the electric field is 0. Make a note of this. So let me know once you're done. Done?
Yes, sir.
Okay. So this the first point, and very, very important point. And the second point is at the surface of the charged conductor, right? At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. This is another property that a conductor exhibits. Okay. So when you take a conductor, for a conductor, right? So what kind of a conductor are you taking? You're not just taking a random conductor, you're taking a charged conductor. So at the surface of a charged conductor, if you try to find the direction of electric field, it will always be normal to the surface, right? So why is it happening? Let's see. Suppose I draw a tangent at this point, and let's say there is an electric field existing like this. Let me call it as E, which is making an angle theta with respect to the horizontal. Now this E can be resolved into this notes, no? So I was writing somewhere. Yeah, I'm sorry. So at the surface of the conductor, the electrostatic field is always normal to the surface. So how is this happening is, if I take a conductor which is charged, right, and let me consider a tangent in such a way that this is going to be resolved into two components. One is going to be E cos theta, and let's say the other is E sin theta, right? So I would like to borrow one point from the next concept. Yeah, this one. The interior of a conductor can have no excess charge, and all the charges will go and sit on the surface of the conductor. This point alone, have it in mind. Why is it so? I'll explain to the next point. The interior of a conductor can have no excess charge in static situation. So have that point in mind, meaning when this is considered to be a charged conductor, all the charges are going to go and sit on the surface of the conductor. So when they sit on the surface of the conductor, had E cos theta existed, right? Had E cos theta existed, then it would have applied force on the charges on the surface, right? That is the first point to be noted. So if those charges started experiencing force, then they would have experienced acceleration. So they would have experienced acceleration means they would have started moving in the first place. So when they start moving, right, this leads to the concept of destruction of electrostatics, because here we are discussing about the electrostatics of conductor. If the charges had started moving, it would have become electrodynamics, right? So if the charges started moving, then the concept of electrostatics would have been violated. As a result of which, what we can conclude is E cos theta is a component that is supposed to be 0, which implies cos theta should be 0 and theta should be equal to pi by 2. Meaning, there is no component that will exist in the direction of horizontal, rather it will exist only vertically, because when theta is perpendicular, when theta is 90 degrees, right, if you substitute it here, you will get the electric field in the upward direction. And this is the reason why we say electric field due to a charged conductor is always perpendicular to the surface at every point. Always perpendicular to the surface at every point. Okay, make a note of this. So done copying this.
Yes, sir.
Good. Third point. The third point states the third point says the interior of a conductor can have no excess charge in the static condition. So it's interior of a conductor can have no excess charge in static condition. So this is the meaning. Let's see what it means. Observe. So if I take a conductor, right, now if I consider a Gaussian surface just below the surface of the conductor, these dotted lines is going to represent the shape of the Gaussian surface, which is just below the surface of the conductor, right? When I take this, I will consider a Gaussian surface in such a way that half the portion is out of the conductor and half is inside the conductor. Right. Now, we know that according to Gauss law, the total flux through the conductor is equal to the charge enclosed by the Gaussian surface divided by epsilon naught. But if you observe, for a conductor, what is the first point that we told? We told that the electric field inside a conductor is going to be 0. When the electric field inside a conductor is 0, can I conclude that the flux inside is also 0? So when it is going to be 0, then that implies that the charge enclosed is also going to be equal to 0. So when the charge enclosed by the Gaussian surface, which was considered just below the surface of the conductor, is 0, it clearly indicates that whatever excess charge that we are giving is supposed to go and sit on the surface of the conductor. So this clearly implies that the excess charge will sit on the surface of the conductor. Okay, so make a note of this point. So done with this. Next point. See, the fourth point says electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. Right, and has the same value on its surface. That is the meaning. So I repeat the point. They're saying electrostatic potential is constant throughout the volume of the conductor and has the same value on its surface. So this is the fourth point. Okay, if I take the conductor, then according to the first point, the net electric field inside a conductor is 0. So we know the relation that E is equal to minus dV divided by dr. So this implies when the electric field is 0, can I write it as minus dV divided by dr? So this clearly indicates that derivative of something that is constant is going to be 0. So from here I can conclude that V is going to be a constant. Okay, so V is going to be a constant. So where is it going to be constant? It is going to be V is constant throughout the interior and on its surface. Throughout the interior and on its surface. Make a note of this one. right? Is it clear? And the fifth point is electric field at the surface of a charged conductor is given by the value E is equal to sigma by epsilon naught times n cap. Okay. So electric field at the surface of a charged conductor is given as E is equal to sigma divided by epsilon naught times n cap. So how does it work? Again, if I take a conductor, right, and for that conductor, I am again considering the Gaussian surface. So we know that the excess charge is going to go and sit on the surface of the conductor. So within this region, let me say this is all going to be positive. Okay. And let me take the area of cross section to be A. We know that the electric field is going to be perpendicular to the surface of the conductor, right? Now, what is going to be the flux here? The flux is going to be E multiplied with A. Similarly, what is going to be the charge enclosed by the Gaussian surface? That will be sigma into A, right? And remember, flux will be equal to the charge enclosed divided by epsilon naught. So what is going to be the flux? E into A will be equal to sigma into A divided by epsilon naught. So A and A will get cancelled. This implies E will be equal to sigma by epsilon naught in terms of magnitude. But the second point already told us that the electric field is perpendicular to the surface. So what I can do is, if I write E as a vector, then we can write it as sigma divided by epsilon naught times n cap. It is going to be sigma divided by epsilon naught times n cap. Okay. So make a note of this point. Am I clear till here? Is there any doubt? Am I clear or not?
Ah, okay, sir. Yes, sir.
Good. Let me know once you're done copying it. Then,
Yes, sir.
yeah. So one last point related to the electrostatics of conductors is this thing. It's called as electrostatic shielding. So as the name suggests, right? So whenever you say shielding, shielding is some protection. So here, the conductor is acting as a protecting material from the static charges. Okay. So if we consider, read the point here, if we consider a conductor with cavity with no charges inside the cavity, then we can observe a remarkable result. That is, the electric field inside the cavity will also be zero. So what are you considering? You're considering a cavity, a hollow space where there are no charges. When there are no charges, obviously the electric field inside is again going to be zero, where a point to be noted is whatever be the shape and size of that cavity, and whatever be the charge on the conductor and external fields in which you can place it. So you place it in the presence of any amount of charge or any amount of electric field, the electric field inside that cavity is going to be a zero. Okay. So if I consider this kind of a system, if I take a conductor, where for the conductor inside you have a cavity, right? In that cavity, what is zero? The electric field is zero, charge is zero, but what is constant? According to the fourth point, the electrostatic potential is a constant. Right? What is going to happen? The electrostatic potential is going to be a constant. As a result of which, this kind of a phenomenon where the cavity is actually protecting us from the outside electric field is what is called as electrostatic shielding. So this is given here. See, whatever be the charge and field configuration outside any cavity in a conductor remains shielded from outside electric influence. The field inside the cavity is always zero. And this kind of a phenomenon that is exhibited by the cavity is what is called as electrostatic shielding. Okay. So what this electrostatic shielding has to tell us, see, let's take another example where you will be able to understand and relate it better. So if you take the lift, right, if you go in an apartment, whenever you try to speak over the call, you will observe that you will not be able to speak. Right? Why is it happening? Because the lift is made up of metal and inside is a cavity, due to which the electromagnetic signals tend to attenuate. Attenuate in the sense they decrease. So when they decrease, you tend to lose the signal. Right? That is another example of electrostatic shielding. Okay. And there is another example that you can think of is, suppose, let's say there is a heavy lightning or a thunderstorm that is occurring, right? So you can put a question like, whenever there is a heavy lightning, right, is it safe for you to stand under a tree or is it safe for you to sit inside a car? So what do you think is the answer? There is lightning, so you will be safe inside a car. Why? Because cars are made up of metals, they are conductors, and inside the conductor, wherever we are sitting, can I consider it to be an example of a cavity? Right. So whatever charge is going to be there, the excess charge will be only on the surface of the conductor, that is on the surface of the car itself. There is no field that is going to enter into the car, as a result of which the electrostatic shielding is the one that is coming into picture, right, during the example that we consider. Whereas when you stand under a tree, right, so there is high possibility you will be attacked by it. Okay, there is a high possibility because of it. So are you able to understand what I am trying to say?
Yes,
Yes,
sir.
sir.
Yeah. So just to summarize, right, we'll come from the beginning. What are the electrostatics of conductors? This is a very, very, very important point. What is the first point that we saw? The net electric field inside a conductor is zero. The net electrostatic field inside a conductor is zero. Secondly, what did we see? Secondly, we saw another important point. What is it? The electric
Electrostatic field is normal to the surface of conductor.
perfect. That's right. Electrostatic field is always normal to the surface of the conductor. What is the third point? You give any amount of excess charge, all the excess charge will go and sit on the surface of the conductor. What was the fourth point? Electrostatic potential due to a conductor. Sorry, electrostatic potential inside a conductor is always a constant, and its value will be exactly equal to the value that is present on the surface of the conductor. What was the fifth point? The electric field, the magnitude of the electric field on the surface of the conductor is going to be sigma by epsilon naught in terms of magnitude. In terms of vector quantity, it is going to be sigma by epsilon naught times n cap. And what was the last point? What was the last point? The electrostatic shielding. Are you able to understand?
Yes,
So,
sir.
all the properties that are related to the electrostatics of conductors, with this, right, we come to the conclusion of electrostatics of, we come to the conclusion of discussing about conductors. The next concept we'll be seeing is the concept of dielectrics, and dielectrics are basically insulators, right? They are non-conducting materials, right? So here, see, this is the concept, that is dielectrics and polarization. Clear? So this one we will discuss it in the next class. But see, as I told you, right, again, I feel like we are spending a lot of time in discussing the theory part, which is simple actually, because I'm taking so much time, like 6 points for me to discuss. It took so much of time today. So what I want to do is, again, like as we discussed the past week, right? Last class, I didn't give you the work because you had a test on 22nd. Now I'm going to give you the work again for tomorrow and Monday. In the sense, I'll be holding the classes for tomorrow and Monday, and I want you to do some homework and come. That homework is from the concept of dielectrics, right? From the concept of dielectrics till the end of this chapter, right? There are recorded videos which are given in module wise, where you can make a note of it, write down everything. I have recorded the same thing again, where you can read it at your own pace. But all I need is, I want you to ensure that you're writing the notes, because I don't see the online class being effective. I'm back only on Tuesday. Okay, on Tuesday, I want to take an offline class because I'm not getting response, and my energy is getting drained. Only one or two are speaking. That is disappointing me so much. I don't know why this is happening. Okay, I'm losing my energy. I'm not able to speak. And that too with the theory that I've already done multiple times, I'm not able to do it. Okay, had it been problems also, I would have enjoyed it. So I'm going to give you work where you need to take from the concept of dielectrics and polarization till the end of this chapter, make notes of everything by going through the pre-recorded videos. And you have time from tomorrow, that is from Wednesday till Monday. Okay. So Monday evening, I want everybody to upload your notes. By Monday, this time, 5:30 p.m., I want all your notes to be uploaded in the app. We will have a look. If you are not writing, right, if you are not writing or you have not done your homework, please refrain yourself from coming to the class. Okay. So from Tuesday, I'll be taking offline class in the center itself. So if you have not completed, please don't. Is the point clear? At least for this, can you guys respond?
Okay, sir.
Is everyone, again, only one is responding? I want
Yes,
to.
sir. Yes, sir.
Yeah. Yes. So again, don't say I didn't tell you all these things. I'm going to drop a message. I repeat it. Tomorrow, I'm holding back the class because I'm not able to take this online session. It's draining my energy like anything by the end of session. Okay. So work on that and come. And you have any doubts? Yeah, you can always approach on the student support number, right? So if there are no doubts, everybody can leave except Pranav. Pranav alone, you can stay back. Others can leave. Others
Thank you,
can.
sir.
Thank you, sir.
Thank you, sir.
Sir.
1 minute. Yeah. One minute.